So on day 5, this is our recap, we continue to talk about lengths on graphs and how each point represents 2 directional lengths on GC. On day 4, we hadn't finished how to animate this, right? So that we could see, for example, we could see this point, we could see this point move back and forth, and then we could actually see the bars move along with them. I actually went ahead and put the solutions to how to make this animation in GC on day 4. So if you want to review that, please go watch the end of the day 4 video. So for right now, after we spent about 10-15 minutes on that, let's continue to what we did at the beginning of day 5. Continuing with lengths on graphs and really being able to see each point, one point, as representing 2 values. Whoa, 2 values by means of 2 lengths on the graph. I handed you either a piece of paper or I sent it to you, I cannot remember which one. But alright, after you did that, we went over the answers, and here are the estimates that I got that you should have close to. For A, y over x is approximately equal to 4. Why? Well, because if we take the x value, if you see this bar, actually let me put it in red. If you see this bar that I'm drawing right here, that is the length of the x value, this is the length of the y value. The y value is about approximately 4 times as large. Here is the x value of b, here is the y value of b. If you take this, it fits in about 3 times. For C, it's about 2.5. If you take this length and you put it down here, so 1 length, 2 lengths, and then about this is how long about 3 of the x value is, right? This length represents the x value. This length represents, going all the way down to the x-axis, represents the y value. Here's x, here's y. Y over x is about 2.5. And what does this mean again? Again, remember, this means that y is 2.5 times as much as x. Okay, and then finally D, this is about 2.3 times, y being this vertical line, is about 2.3 times as large as the size of x. So then I asked, what do you notice about all these numbers? Anything special about them? One person said they decreased, and I said, exactly. Look at this. Are these all the same number? No. Is it always that y is the same number times as large as x? Y is the same number times as large as x on a line? Absolutely not. Sometimes it's 4 times as large, sometimes it's 3 times as large, sometimes it's 2.5 times as large. This is 100% not true. Not true. And I said, alright, well, instead of y and x, what about calculating the relative size, or how much bigger the change in y is compared to the change in x? And so I said, alright, from A to B, I want you to estimate how much x changes and how much y changes. For dx and dy, draw bars whose lengths represent dx and dy. Just like before, we had drawn bars whose lengths represented x and y. Now we're doing dx and dy. And again, I gave people time to work on that. Alright, so then we were ready to go over the answers. This time, you don't take the whole bar of this, so let me show what y would be like. This is y, right? But only this much is dy. That's all that changed as we go from A to B. Similarly, this is the x of B, but only this much is the dx. And so if we look at dx and dy, we say, oh, dy is about twice as big as dx when you go from A to B and A to B. What about when we go from B to C? Change in x, change in y. Well, change in y is about 2 times as much as change in x. If you go ahead and calculate these, you'll find that actually, for any change in points from A to B, or from B to C, or from C to D, or from A all the way to C, the ratio is always 2. I'm going to actually erase something right here. We don't want to use the delta right now, we want to use D. The ratio is always 2. The change in y is always twice the change in x for each one of these situations. So, for any point, y is not always, and I gave people time to try to fill these in, and then we went over them. Y is not always the same number times as much as x. But for any point, oops, let me erase that. But for any point dy is always two times as much as dx. What is common is not the relationship between y and x. What stays constant is the relationship between dy and dx. This is something really common that people miss up, which is why I'm going over it and over it again. Y over x? Nope. Y is not always the same multiple of x. Dy over dx? Yes. Dy is always, in a line, the same multiple of dx. So we ended today with going over a couple of examples from Chapter 1 and Chapter 3. So one question that people really had was on number 1.1.2, where the figure shows the vertical axis being stretched until finally you get so zoomed in on this graph that the top value of the graph shows a value of 6 times 10 to the negative 64. Right there. All right. So then it says use a measure to ruler to measure from 0 to 6e to the negative 64 on your screen. Maybe that's about 4 centimeters on my screen. How far is 1 from the horizontal axis? In other words, you imagine 1 somewhere way up here, right? We want to figure out how far that is. Okay, it comes back to the idea of measurement of how many of one thing fit into another thing. How many of these, let me actually put the second one in blue. How many of the red length fits into the blue length? How many of the distances from 0 to 6e to the negative 64 are going to fit into the length from 0 all the way to 1? Well, the answer to that is the distance from 0 to 1, which is 1, divided by the distance from 0 to 6e to the negative 64, which is 6e to the negative 64. Don't forget that this is the same as 6 times 10 to the negative 64. Alright, so right here is number of times the length, whoa, can't spell today, the length of length of red bar, right here, from 0 to 60 to the negative 64, fits into blue bar, which is the length from 0 to 1. Alright, well, if that's how many times it fits in, that's how many copies, well, each of those copies are going to be 4 centimeters. So if we multiply that by 4 centimeters, now this gives me how far, this is how far 0 is from 1 in centimeters. From then on, you can go ahead and convert to light years, but the important thing is to be able to say, oh, I can chop this up. How many of this length fits into this length? Oh, that's caused by dividing the length I'm trying to measure by the length I'm measuring with. Okay, I'm going to erase this and show one more example. For problem 3.1.1 CD, several students struggled to express the relationship between the length and the width symbolically. Keep in mind that the perimeter stays at a constant 240. So some people said as the width increases, the length decreases, things like that. All of which are true, but if you want to express a relationship symbolically, that means you need an equation that relates them. So let's figure out how you would find the width given the length. Let's say I have a particular length, and I'm going to use an example that I call the fake number strategy. Alright, I'm going to just say this length is 10. Okay, in which case, how would I find my width? Well, I know that the length, there's 2 of them, so that takes up 2 times as much as 10, right? That's how much is used up of my perimeter for the lengths. Well, then how much is left for the widths? Well, I guess I need to take this and subtract it out of 240. Right? This now represents, I'm going to use a different color here. This now represents how much I have for both of these sides. Both of these sides. Alright, but that doesn't tell me the width. That tells me how much 2 of the width is. So now I need to go ahead and divide by 2. And that gives me the width. So now what would I do if this wasn't 10, but instead this was any number? Well, I would do the same thing over here. I'd say, oh, well, if this is any number L, then 240 minus 2L all over 2 will give me the associated width. So this is the answer to what it means to express the relationship symbolically. And there is where we ended day 5. I will see you. 6 and 7 are already taped, so I'm going to also do recaps for days 8 and 11.